Good morning, everyone. Myself Jayesh Naik, and today I'll be explaining the topic of design of earthing grid for substation. An earthing grid plays a vital role in substations where large fault currents and high voltages are involved. Its main purpose is to ensure the safety of personnel and equipment by providing a low resistance path for fault currents to flow safely into the ground. In this presentation, I will be covering the objectives, requirements, design procedure, and components of the earthing grid system. I'll also explain how it helps to maintain safe step and touch voltages, ensuring reliable operations of the substation according to IEEE standards. Overall, this topic highlights how proper earthing design forms the backbone of electrical safety in power substations. So the main objectives of an earthing systems are first to protect both people and equipment from electrical hazards. Second, to safely dissipate fault currents into the earth to prevent dangerous potential differences. It also ensures that step, touch, and mesh voltages remains within tolerable limits and provides a common reference potential for all electrical systems. In short, earthing ensures that any fault current flows through a low resistance path instead of through human bodies or equipments. So why there is a need of earthing mesh or earthing grid? So in a substation, fault currents can be very large, often tens of kiloamperes. So a simple pipe or plate earthing system cannot safely handle or dissipate such high amount of currents into the ground. The earthing grid or earthing mat spread this current over a large area, reducing the overall resistance to earth and ensuring the voltage rise on the ground surface remains within the safe step and touch potential limits. So the earthing grid is needed to safely dissipate used fault currents into the soil, to maintain uniform potential across the substation yard, protect any person working on there, provide multiple parallel paths for current flow, to bond all metallic structures like transformers, breakers, and isolators to one common reference potential. For an earthing grid to be effective, it must satisfy certain requirements. It must provide safety by maintaining step and touch voltages within limits and controlling ground potential rise. It must have good electrical performance, which means the grid resistance should typically be less than 1 ohm to ensure proper fault dissipation. It must also have mechanical strength to withstand high fault currents and durability against corrosion using copper or galvanized iron. Lastly, it should cover the entire substation area, connecting all metallic structures and equipment bases. The design follows IEEE standards 80-2013 and IS 3043-1018. The earthing system is made up of several components. This includes earth reactors like vertical rods. The ground grid consists of threaded interconnected conductors and the earth mat under the substation surface. We also have earthing leads connecting equipment to the grid and enhancement materials like charcoal that improves soil conductivity. All these components work together to maintain a low resistance path to earth. When designing an earthing grid, several parameters must be considered, which are fault current IF, which is the maximum current expected during a fault. The fault duration usually 1 second. The soil resistivity rho measured by the Venner 4-point method, and a layout dimensions of substations. We also consider the step and touch potential limits to ensure operator safety. So to maintain safety, we compare calculated voltages with tolerable limits as per IEEE standards. These are the formulas where ρS is the surface resistivity and Cs is the deteriorating factor for surface material like gravel. If the actual voltages are below these limits, the system is safe for human contact. The first step in designing is to determine all input parameters like fault currents and its duration, soil resistivity from the 4-point test, and the physical dimensions of the substation area. Accurate field measurements are important because soil resistivity varies with moisture, temperature, and depth. So the second step is to select preliminary grid layout. The grid depth is generally between zero point 0.5 to 1 meter below ground. The grid spacing can vary from 3 to 10 meters depending on soil resistivity and safety requirements. We use copper or galvanized steel conductors and always includes a perimeter conductor to maintain uniform potential distribution. So the third step is to calculate the grid resistance. The resistance of the entire grid is calculated using the following formula, where rho is the soil resistivity, A is grid area, and L is the total conductor length. Our goal is to keep the resistance less than 1 ohm, ideally around zero point 0.5 or lower, to ensure quick dissipation of fault currents. The fourth step in designing is to calculate the ground potential rise (GPR). The ground potential rise or GPR is given by multiplying fault current by grid resistance. It represents how much the grid potential increases during a fault. We must ensure that GPR does not exceed the safe step and touch voltages levels. Otherwise, a person standing near grounded structures may be exposed to danger voltages. The fifth step in the designing is to verify safety criteria. We have to ensure that touch voltages and step voltages are within the tolerable limits. If they are not, then we can improve the design by increasing grid area, adding vertical rods, reducing soil resistivity with chemicals, or using a gravel surface layer to increase insulation. Let's take an example for a thin grid for 132 to 220 kV substation. These are the given datas. From the given data, we can deduct a summary of design features. In this design example, the substation has a grid area of 25 by 10 meters and a grid depth of 1.2 meters. Having conductor spacing of 2 meters, the total buried conductor's length is 248 meters plus rods, which is 308 meters. The calculated grid resistance is 0.0255 ohms. This value is excellent and ensures that both step and touch voltages remains within the safe limits. So now let's see the step-by-step calculations for the given problem. First, we have to calculate tolerable touch and step voltages, for which we have already seen the formulas. Then we just have to substitute the values from the given data, which is rho, which is the soil resistivity given as 25 ohm meter, and the time duration for the leakage current, which is 0 0.5 seconds. After substitution, we got touch and step potential values. So next we will calculate allowable grid resistance, which is R max. We have the formula E touch upon the IEFS, where IEFS is leakage current or short circuit current. We have the values from the given data, and by calculation we got to know about the R max value is to be 0.0269 ohms. Then we'll calculate ground rod resistance for a single rod, for which we have this formula, and we assume D is equals to 0.04 meters, which is nearly 40 mm rod. So substituting this value of D in the equation, we got this equation. And for 12 rods in parallel, we calculated the resistance to be 0.3456 ohm. Next, we will calculate grid resistance for horizontal conductors using the IEEE simplified formula, which is shown, and by substituting the given data into the formula, we have the resistance value is 0.0273. Then we have to calculate total grid resistance combined with rods. Means grid resistance and rod resistance combined all together. For parallel combination, we have this formula. And by substituting the given data, the resistance is to be 0.0255 ohms. Then we have to calculate grid potential rise GPR. So as shown earlier, the formula for GPR is for current into resistance, which is 1020 volts. Now we have to do safety verifications. As we have calculated the touch and step potentials, which is this, and as we can see, they are well within the limit of GPR. So it's better to say the system is safe. Now, once we have calculated all the parameters and their values, let's make a result table. Here are all the values with their formulas and with their units. So the final result shows a grid resistance of 0.0255 ohm and a potential rise of about 1020 volts, which is below the permissible limits. Thus, the design is considered safe and complement with the IEEE standards and requirements. So to optimize the performance, we can increase mesh density for better potential, uniformity, and more electrodes, or use soil enhancement components to lower the resistivity. Adding a crust rock surface layer also helps by providing high surface resistivity and reducing the step voltage. All the metallic equipments must be properly earthed, means the transformers, neutrals are connected directly to the grid. Lightning arresters have the shortest possible path to ground, and control panels are grounded via copper strip. Proper earthing ensures both function and productive grounding in substations. The main materials include copper or GI conductors of 25 by 3 mm size or 95 square mm cable, GI or copper rods of 3 to 5 meters, exothermic welding or clamps for joints, and crushed rock for the surface layer. The material are chosen for strength, conductivity, and corrosion resistance. This design follows international standards IEEE Standard 80, Safety in AC Substation Grounding, IS 3043, Code of Practice for Earthing, and IEC 60364 for protective conductors and earthing systems. Following this ensures the global safety compliance and reliability. We also have some practical considerations. So in practice, it's also important to avoid corrosion by using similar metals. Check joint integrity regularly and maintain low resistance periodic testing. A well-maintained grid remains reliable throughout the life of the substation. We also have to perform testing and maintenance. We perform regular earth resistance tests using the three-point method and visually inspect connections for corrosion or damage. Enhancement materials like bentonite may need to be reapplied periodically to maintain the performance. After the designing, we have to take some safety measures. which includes maintaining a gravel surface to increase insulation, fencing high potential areas, and leveling all grounding points clearly. This ensures the operator safety under fault conditions. Now to conclude, proper earthing designs ensure safety, reliability, and long-term operations of substation. By following IEEE and IS standards, using corrosion resistance materials and maintaining the system regularly, we can protect both equipment and person from electrical hazards. So that's why designing the earthing grid and maintaining it's crucial.